All right, I think we're recording. Okay, so we're going to talk about average value of continuous functions today. But before we do that, I want to flash back to one of the formulas that was on the formula quiz that you guys just took. Mean value theorem. So what does the mean value theorem say? If a function is continuous on a closed interval and... Oh, you're skipping something. There's one more condition. It has to be continuous on a closed interval and differentiable on an open interval. Okay, so let's draw that picture. A function that is continuous on a closed interval and differentiable on an open interval. Continuity is part of differentiability, so that part's taken care of. That also means that we have no points where we have, or no places on that graph where we have like a sharp point causing the derivative not to exist, or like a vertical tangent line that would cause the derivative to be undefined. So we have a function that is both continuous and differentiable on a closed interval from A to B. If that is true, then what else is true? There exists a number C between A and B such that nope, not f of C equals K. That's intermediate value theorem. F of C does have to be in between A and B, so there exists a C value, at least one C value, somewhere in that interval between A and B, such that has to do with the derivative. The derivative at the point C is equal to f of B minus f of A over B minus A. What is f of B over f of A minus B over B minus A? That's the slope between the endpoints, right? The slope of that line is f of B minus f of A over B minus A. So we're saying that somewhere in between A and B, there is at least one number where the derivative at that point is equal to the slope of that line. And the derivative is what? Well, what else do we think of when we think of derivative? Derivative is also... that would be the second derivative, acceleration. Derivative is also slope. It's the slope at a point. It's the slope of the tangent line at a point. Would be the slope at a point. So we're saying that there's at least one value C where the slope of the tangent line is the same as the slope of the line that runs through the endpoints. At least one. Could be more than one. This graph would actually have 2 points where that would be the case. I didn't do a very good job drawing the second line. In other words, there's at least one point where the slope of the tangent line is the same as the slope of the secant line that runs through the endpoints. That's what our mean value theorem says. So we're going to add to that another mean value theorem. The mean value theorem for integrals. Well, when we think of derivatives, we think of slope. When we think of integrals, what do we think of? Amount or antiderivative, or what is it that we've been calculating with definite integrals? Area under a curve. So the mean value theorem for derivatives has to do with slope, because that's what a derivative is. The mean value theorem for integrals has to do with area. So if a function is continuous on a closed interval from A to B, A, B, continuous on the closed interval from A to B, then there exists a number somewhere in that closed interval from A to B, we can call that number C, such that the definite integral from A to B of f of x dx is equal to f of c times b minus a. Okay, well, let's see if we can break this down and try to understand what this is saying. This definite integral from a to b of f of x with respect to x is equal to what in this graph? The area under that curve from a to b is equal to f of c times b minus a. Well, let's start with the b minus a. What is b minus a going to give me? The width of the interval. So b minus a is that length. If I multiply that times some number c, or f of c, let's say c is here, what would f of c represent? A height. So what am I doing? Well, I'm multiplying a base times a height. More like a rectangle than a triangle, right? That's exactly what we're doing. That's the area of a rectangle. In other words, there is an x value somewhere in that interval between a and b, where you could build a perfect rectangle, a rectangle whose area is exactly equal to the area bounded by f of x in the x-axis. Mean value theorem for derivatives says that there's at least one point in the interval where the slope of the tangent line, the derivative at that point, is equal to the slope between the endpoints. Mean value theorem for integrals says there's at least one point between a and b where the area under the curve from a to b, if I evaluated the area at that point, the width and the height of the area of that perfect rectangle, those would be equal. Value theorem for derivatives, there's at least one point where the slope is equal to the slope of the whole thing. Mean value theorem for integrals, there's at least one point where the area of the rectangle is equal to the area of the whole thing. That's what we're saying there. You okay with that? That value, f of c, from that mean value theorem for integrals is called the average value of the function on the closed interval from a to b and is denoted as f average. Fave. F average. So this is the average value of the function. Well, if we took this integral to solve it for the average value of that function, we'd have to get rid of the times b minus a. So to get rid of the times b minus a, we multiply by 1 over b minus a. And so the resulting value for f of c is 1 over b minus a times the integral from a to b, f of x dx. That's our formula to find the average value of a function on a closed interval. Bless you. Any questions about that formula before we use it? We solved this for f of c. F of c is the average value. So if I multiply both sides by 1 over b minus a, I have f of c, the average value of the function. Average value. That was the mean value theorem. The value, that point, f of c, that f of c value is the average value of the function. In other words, if I look at every single value that the function attains between a and b, and there's an infinite number of them, but that's okay because this integral does exactly that, adds an infinite number of function values. And if I divide that by the width of the interval, I get the average value that the function attains on that interval. In other words, thinking of what average means, if I could take every single function value from a to b and divide it by the infinite number of function values to find the average value, it would be that. Okay, let's look at an example. Let's say f of x equals x minus 3 squared, and we're looking at that function on the closed interval from 2 to 5. We want to find the average value of f on the given interval. Let's see. So the average value of f is equal to 1 over b minus a, 5 minus 2, times the integral from a to b, 2 to 5, of f of x, x minus 3 squared, with respect to x. So I have 1/3 times, we are going to do this by hand. If I'm doing this by hand, I could expand that, or I could do u substitution. Let u equal x minus 3. So then du is dx. So I have 1 over 3 times the integral of u squared du. Since I've changed my x's to u's, I'm going to go ahead and change all of my x's to u's. If x is 2, then u is 2 minus 3, negative 1. And if x is 5, then u is 5 minus 3, which is 2. So that's the definite integral of u squared from u equals negative 1 to u equals 2. So I have 1/3 times, oh, sorry, yeah, I did say one thing and write something else. I've been doing that a lot lately. My brain is not working right. 1/3 times u cubed divided by 3, evaluated from negative 1 to 2, or 1/9 times u cubed, evaluated from negative 1 to 2. 2 cubed is 8, minus negative 1 cubed is negative 1. So I have 1/9 times 9. So the average value that the function x minus 3 squared attains between 2 and 5 is 1. Any questions about that? Okay, I'll give you a second. Give me a second to catch up and process. What part? That is 2 cubed is 8, minus negative 1 cubed is negative 1, minus the negative 1. I'm actually applying the fundamental theorem at that point. And evaluating the antiderivative at my upper bound 2 minus the antiderivative at my upper bound negative 1. I factored the 3's out. Yep, that's f of b minus f of a, exactly. Any other questions? That's really not a long process. Just wait till we get to solving differential equations. You haven't seen a long process yet. I don't even know what a long process looks like at this point. Actually, you kind of do. Think about going back to the definition of derivative and evaluating it using that limit. That was a long process. This, few basic derivative rules. Exactly. Okay, so part B says, okay, now that you know what the average value is, find the value of C where f of C is equal to that average value. In other words, this is, that one is f of C. It's the function value at some point. Figure out what point C between A and B that happens at. This is equal to f of C for some C value between 2 and 5. What C value? Well, We want to know where is f of c, also known as x minus 3 squared, equal to the average function value, 1. And not just anywhere, it has to be a c value between 2 and 5. So if we take the square root of that, the square root of 1 is not 1. It's plus or minus 1. If we're taking the square root, it could have been a negative 1 because when we squared it, we would have gotten positive 1. So if I add 3, I have 3 plus 1 would be 4, and I have 3 plus negative 1, which would be 2. If I have positive 3 and I add 1, I get 4. If I have positive 3 and I add negative 1, I get 2. Both of the numbers are in the interval, because notice that in the mean value theorem for integrals, the endpoints can be included because it's a closed interval. So we have two, well, we said at least 1. Doesn't have to be exactly 1, at least 1. In this case, we actually have 2. And in part C, we're going to see why that is. So C could be 2 or 4. Oh, it is Groundhog Day tomorrow, isn't it? If he sees his shadow, there's 6 more weeks of winter. Considering what's happening in like the rest of the country right now with like negative 50 degrees, I think that he's not even going to come out of that hole. He's going to be like, nah, it's too cold. I'm staying in here, guys. I'm good. Okay. Part C says, okay, now sketch the graph of f and that perfect rectangle whose area is the same as the area under the graph of f. So we know that this is a parabola with a vertex at 3, 0. See, we'd have a point here and here, and then, so our function looks something like that. And we're only interested in the closed interval from 2 to 5. So we're talking about when we evaluated that integral, we found that area. We're saying that if we draw a rectangle whose width is the same as the width of our interval, so 2 to 5, the height of that rectangle would need to be f of 2 or f of 4. Do you see why there's 2 points? Because they're the same value. The area of that rectangle is the exact same as the area under the graph, between 2 and 5. I don't know who figured that out. Somebody way back in the day. You could Google it. Who discovered the mean value theorem for integrals? Maybe I'll look that up while you guys are... Yeah, that was breakfast. Do y'all have any questions about that first example? Are we good there? Say that again? Those areas are exactly equal to each other. So if we looked at the area under the graph of x minus 3 between 2 and 5, and we look at the area of that rectangle, those areas are exactly the same. Exactly the same. Here's why. Look. The area under the graph from 2 to 5, we'll use our calculator to show it. The area under the graph from 2 to 5 is the definite integral of x minus 3 squared with respect to x, starting at 2, stopping at 5. 3. Okay, so what is f of 2? Well, f of 2 is x minus 3 squared such that x equals 2. 1. Or at 4, we also get 1. So the height of that rectangle is 1. The width of that rectangle is 1, 2, 3. the area of that rectangle is also 3. Crazy. All right, so while you guys are getting breakfast, I'd like for you to try this next example. Actually, go ahead and try the next two. You can use your calculators on these. So, by the way, it's number 7 because this is number 7 from the worksheet you guys got whenever I passed them out earlier. So, number 7 from the worksheet gives you a table with values for a continuous function f. Use a midpoint Riemann sum to estimate the average value of f from 20 to 50. So you're going to have to approximate the definite integral by using a midpoint Riemann sum. We reviewed that yesterday. Then in number 9, they tell you that in a certain city, the temperature in degrees Fahrenheit, T hours after 9 a.m. was modeled by the function T equals 50 plus 14 sine of pi times T divided by 12. Find the average temperature, the average value of capital T from 9 a.m. to 9 p.m. You'll use your calculator, so set up your definite integral and use your calculator to evaluate it. Any questions before I let you guys try those? Because the little t is time and the big T is temperature. Call it something else if you want. Call it something else if you want. Call it whatever you want. Call it whatever you want, as long as you find that right value. Any questions before I let you guys try this? All right, go ahead and give it a shot.